our next presentation with Arthur Endsley. Arthur is a researcher in University of Montana. We have been collaborating recently, I mean, the last, what, 2, 3 years, I don't know. Arthur also came to Algeria. He made some training, and he's working now. He will be presenting more about the his research work on the modeling of, I mean, ecological modeling and remote sensing. So, I mean, the floor is for you, Arthur, whenever you want. If you can share your screen, maybe just to test, and we'll move on.
Yes, thank you, Waleed. Okay, are you able to see my screen?
Yes.
Okay, let me just try and hide some of these
Yeah.
things. Get that out of the way. Okay, and then let's see if I can. Oh, nope, I've encountered this issue before. I need to actually put this in presentation mode first. Okay, and now I should be able to share.
Um, we lost Arthur, I guess. So I can share his screen, his slides actually. Let's see if this may be a better way. Arthur, I shared your screen. I shared your slides. I'm not sure if this is better for you, or you wanna still try to share again from your side.
I think I'll try
Okay, let me
one
stop
more
then
time
sharing.
here.
Okay, go ahead.
Yeah.
If you
Okay. Try to get everything out of the way. And then, okay.
yep, this is much better.
Okay, so my name's Arthur Endsley. I'm from the University of Montana. It's going to be hard to follow Natasha's talk because she's already talking about yields and production and agricultural ecosystems. But hopefully I can provide maybe a view of some of the modeling that underpins those yield models and how we also use remote sensing to integrating data into these models. So my background's in ecology and remote sensing, but my work today is generally in modeling ecosystem function and ecosystem fluxes of carbon and water. And so for my talk, I'm really concerned with, why ecosystems, why modeling, why remote sensing. Um, that's kind of the perspective I'm going to be taking today. So with that, um, I want to first introduce the idea of the ecosystem concept. I know we've got some practitioners in the audience, so why would it be useful to consider agricultural systems as ecosystems? Well, there's an advantage to this viewpoint. In ecosystem ecology, we have explicit consideration of plant metabolic and physical requirements. So those field measurements and measurements and models by plant physiologists directly inform our models of plant function. It also permits us to describe how environmental constraints can predict the distribution, growth, and reproduction of plants. It entails the explicit quantification of matter and energy pools, such as water, and the fluxes that we're interested in, which would be a yield of carbon from an ecosystem, yielding the fruit or the cereals or whatever we're seeking to extract from the ecosystem. And then it also allows us to identify the most limiting factors to plant growth. And as an example of this, this is an example from work that was done in my lab over 20 years ago, but we still use these kinds of modeling frameworks because they're extremely useful. we were able to quantify using kind of the first global model of gross primary production, which I'll talk about in a moment here. We were able to actually identify the most limiting factor to primary productivity. And you can see from this map, a lot of it is as you would expect. And in much of the tropical regions of the world, those ecosystems are largely limited by radiation. So those are more humid environments where it's cloudier. This modeling suggests it's kind of in line with our intuition and ecophysiological theory that the real limiting factor to boosting primary productivity in those environments is just getting more sunny days, getting more solar radiation. And then in other environments, you can see that it could be maybe temperature is more limiting. Certainly in semi-arid and arid regions of the world, water is more limiting. And from an ecosystem ecology framework, we're trying to identify these limits to productivity. So that can be helpful for agronomy and agronomists as well, to understanding what's limiting yields or what's limiting production. So another perspective that I bring to this is that of process-based models or physical models of ecosystems and ecosystem processes. So I want to share here just an example from the Century model. This is a model of soil organic carbon dynamics. I'm not going to go into a lot of detail about this model, but essentially we have carbon entering soil pools as litter fall. There are 3 different soil pools in that kind of middle row of boxes. And these are determined by how long it takes carbon to turn over in that particular box. And then a fraction of that carbon is sequestered in soil organic matter at the very bottom. And so why might a process-based model like this be useful for understanding agricultural ecosystems? Well, there are several advantages to this kind of approach. I mean, for one, this model is modular. I could decide to add some additional soil organic carbon pools. I could decide to remove some. It should be pretty obvious how to do that from this graphical depiction. This model is also traceable. If I want to understand the change in soil organic matter in the SOM1, that lower left-hand box, the first soil organic matter pool, well, I understand that it is getting carbon contributed to it from the labile pool of litterfall. And that ultimately is determined by the total amount of litterfall that this particular ecosystem produces. So I can trace I can do a sensitivity analysis. I can trace the flows of matter and energy in this model. This model is also explicable. It's hopefully easy to explain. I really like this graphical depiction of it. I think it makes it pretty easy to understand. This model is also differentiable. And in this way, I mean, I'm making an analogy here with a neural network. So this is a directed acyclic graph, and we could actually calculate, again, as part of a sensitivity analysis, we could calculate the rate of change in carbon entering the soil organic matter pool for a certain change in litter fall or a certain change in the turnover time. So in this sense, we could actually fit this model using the same kinds of backward propagation techniques that we use for neural networks, the same kind of analysis techniques that we use for directed acyclic graphs more generally. And then ultimately this model is transparent. Again, getting to the visual nature of these kinds of model depictions. This is not the kind of graph that you can create for, say, a machine learning model, which is typically just a black box. And I think that process-based models have another advantage over pattern-based models or machine learning models, in that machine learning models are easily surprised. So this is one of my favorite examples from a recent study that compared different process-based models and machine learning approaches and satellite-based indices for their ability to predict the trend in global gross primary production and the global carbon sink, and in this case, the growth in the global carbon sink over time. And what you'll notice from that left-hand series of plots, those 3 time series plots, is for most of these approaches, a satellite-based index or an Earth system model or land model or dynamic global vegetation model, we do see an increase in gross primary production over time. And this is consistent with what we know about terrestrial ecosystems, about CO2 fertilization, about global greening. But you notice there is a flat line in those time series, and that is the one machine learning product that was included in this analysis. So very clearly, this machine learning model, which is an ensemble tree model like random forest, it's only capable of learning these cross-sectional relationships. It's not capable of predicting this secular trend that we know is quite real, and we see it in these other products. So there are ways to account for that and to include sensitivity to those features in a machine learning model. But it is not something you get for free, and it's something that takes a serious thought and consideration. Whereas a process-based model is a much more explicit representation of our knowledge of the system, and it's much easier to identify what is or what is not embedded in that representation. And then the last component is remote sensing, right? So why is remote sensing so useful for understanding ecosystem processes and ecosystem function? And well, that's because many of the things that we care about that are changing in ecosystems are things that we can resolve from space with spaceborne sensors. So this is a depiction of the electromagnetic spectrum. We have a number of sensors that are sensitive to broad segments of the electromagnetic spectrum at microwave wavelengths. We are sensitive to temperature and moisture, and we have microwave radiometers that are currently capable of measuring soil temperature and soil moisture and even vegetation moisture. At infrared to visible wavelengths, we now have the multi-decades of measurements from Landsat, from the Earth observing system. And at these wavelengths, we're sensitive to water content. We're also sensitive to biophysical compounds in leaves like chlorophyll and starches. And then also at the high energy edge of that visible spectrum, we also have LiDAR or laser altimeters. And this gives us information about canopy height and canopy closure and other metrics that allow us to estimate biomass in ecosystems. So remote sensing plays a key role in providing information that is input to ecosystem models. And just to provide another more concrete example of that, there's a recent NASA mission. This was launched last year. So we don't have a good longitudinal record with this particular mission, the NASA PACE mission. And this mission actually was designed originally for monitoring the ocean and for ocean science. But they've recently developed a suite of land products, which are really impressive because this is a hyperspectral sensor. So it is sensitive to a broad section of the visible near-infrared and shortwave infrared spectrums. But it also has very high spectral resolution. So it's able to take several closely spaced samples or measurements within those spectra. And that allows it to, they've developed products, as you can see here, related to chlorophyll, to carotenoids, to anthocyanin. So there's a number of, these are products actually, you don't even have to calculate them. You can just download them from this mission. So I think this is really underutilized. The spatial resolution is a little coarse, but it shows what we can do with hyperspectral remote sensing, which is becoming much more common. We have many more hyperspectral platforms that are being launched. So when we talk about modeling agricultural ecosystems, the major interest, and probably what a lot of the previous speakers in this workshop have been talking about, include evapotranspiration and some measure of vegetation vigor, such as the normalized difference vegetation index. A lot of this is driven by the promise of so-called precision agriculture. We're interested in ET because it supposedly tells us how much water to put on the plants, and we're interested in measures like NDVI because it supposedly tells us how water stressed the plants are. I'm going to argue that these are imperfect ways of understanding agricultural ecosystems. Evapotranspiration, of course, encompasses all fluxes of water from the ecosystem, including from soil and from intercepted water. So it's not quite a measure of water use, and there are some difficulties modeling it that we'll discuss. And then when it comes to vegetation vigor, spectral indices like NDVI, I'm not going to talk about them much today because really, what do you do with NDVI? It's a dimensionless index, We know that it's monotonically correlated with water stress, but we don't know exactly what thresholds or what kind of measurement along that index is really informative as to what plants in this particular agricultural setting are doing right now. So I'm going to talk about these issues through the lens of 3 modeling studies based on my work. So I'm going to talk about modeling evapotranspiration with the MODIS Mod 16 model. It sounds like there are some people who are interested in agroforestry. I don't know if there's anybody who's interested in rangeland or livestock production, but I'll talk about how we model rangeland forage with the MODIS Mod 17 product. And then finally, I'll talk about a relatively recent mission and model that allows us to actually predict crop conditions and crop yields. So to start with evapotranspiration, my favorite definition of evapotranspiration actually comes from Monteith's paper in 1965. And I don't like to use a market analogy for everything I want to talk about, but this one I thought was just really good. ET is like a commercial transaction in which a wet surface sells water vapor to the environment in exchange for heat. The environment supplies that heat by solar radiation, by turbulent transfer of heat from the atmosphere, or by conduction from the soil. And indeed, that is what we're talking about when we're talking about evapotranspiration. We're talking about a latent flux of heat, or lambda E. So in water balance terms, precipitation is the major source of water to ecosystems. We have a change in groundwater storage. We have runoff. Evapotranspiration is the major flux of water out of that ecosystem. But when we model this, we can actually model it as a water flux or as an energy flux, because the production of water, the movement of that water, the driving force of moving that water through plants and out of the ecosystem is energy. And it's energy from the sun in the form of shortwave radiation. It's energy from the atmosphere and from the ground in terms of long wave radiation, closer to thermal wavelengths, and also that ground heat flux. And so one of the approaches, as we'll discuss, to modeling ET is to quantify it as part of a balance of energy. So balancing the energy that's coming into the ecosystem with the sensible heat flux, the heat that you can actually feel moving out of an ecosystem, and then the ground heat flux being the energy that the ground absorbs and moves away from the immediate environment. So approaches to modeling ET have varied over the years, but the major developments that I think are worth discussing include water balance approaches. So similar to what I was just talking about with an energy balance, we could quantify the upper limit to ET, so the maximum amount of ET that could be produced based on the available energy. We call that potential evapotranspiration. And in fact, the first generation of biosphere models took this approach. So we take that upper limit and then we multiply it by a factor called beta, which has a significance that spans multiple generations of ET models. The same coefficient beta has been modeled in different ways because this really represents the evaporative fraction that we'll talk about later. It's essentially determined by what kind of ET regime we're in, whether water or energy are more limiting to the ET flux. The second generation of ET modeling approaches really began with the surface energy balance approaches, where they tried to explicitly constrain the net radiation that's input to the ecosystem, the sensible heat flux out of the ecosystem, and the ground heat flux too, which is small but important in some ecosystems, particularly dry or very hot or very cold ecosystems. That ground heat flux can be a significant source of energy to drive more ET, energy to reduce ET. And these approaches really...
I think if you hear us after you're freezed, wait a little bit and then let me take.
Sphere continuum as a series of resistances. So there's various resistances to that water flow from the surface to the atmosphere. And indeed, a number of popular ET models that are still in use today take the surface energy balance approach, such as SEBS, Siebel, or metric, which are used in the OpenET ensemble. And then the third generation of ET models includes what I call the micrometeorological approaches. So I'll talk about some specific models in this generation of models, but they all share some similar features, and they all really began with the recognition that plants and the vegetation surface plays an active role in regulating the ET flux. Transpiration is a major part of evapotranspiration, and so plants through stomatal control can actively regulate ET. These were also the first generation of models that considered multiple water compartments, where we have water evaporated from the soil, we have water evaporated from the canopy, and then we have transpiration, or the flux of water through the xylem of plants and out through plant stomata. These micrometeorological approaches generally take an approach where we know there are these various constraints or drivers of ET, the input radiation, the vapor pressure deficit, the temperature, but we don't know the exact functional relationship between some of these drivers and ET. And so one of the innovations that made this generation of models possible was really Jarvis and Stewart, who introduced this boundary line analysis, where in this example, on the vertical axis, we have actually stomatal conductance normalized by its maximum value, but essentially what we're trying to do is model the response of evapotranspiration to temperature, or model the response of evapotranspiration to VPD. And these are two example functional forms that we might choose based on the distribution of ET measurements, or stomatal conductance measurements. And it's normalized in this way because these functions are assumed to be independent. They need to be independent. We know that there actually, of course, is an interaction between temperature and VPD and soil moisture and radiation and other drivers. But for this particular mathematical approach, they need to be independent. And so this normalization allows us to draw essentially the upper limit to that response. So really where that driving factor starts to become limiting to ET. And the two models that you may have heard of that are associated with this micrometeorological approach are the Penman-Monteith and Priestley-Taylor approaches. And these are two different strains of research that emerged from that recognition of the importance of plant stomata and plant regulation of ET. The Priestley-Taylor approach represents a strain of research that is really interested in quantifying potential ET based solely on weather variables, whereas Penman-Monteith, on the other hand, tries to estimate the vegetation canopy resistance. And the FAO, in the seminal FAO 56 guide that many of you are probably familiar with, that is a kind of guideline for modeling ET throughout the world, and particularly in agricultural settings. They picked the Penman-Monteith approach for general application to global croplands. This is usually done, again, with these driving climate variables, some kind of reference crop, usually a well-watered, low-stature vegetated crop, in order to predict potential evapotranspiration. So the Penman-Monteith approach is popular because it was really Penman who first demonstrated that we can estimate evapotranspiration using climate data. And then Monteith came in and first eliminated surface temperature from the surface energy balance equations. That was really important because it was very difficult to really measure that. And then demonstrated how to estimate canopy and aerodynamic resistances. Again, two of the resistance.
It's unfortunate. I don't know if you have it too, but it's blocked at a certain point. not me, text Arthur to send.
To estimate
Arthur,
evaporation at scale. Yes.
I'm sorry to interrupt you, but you were blocked at certain point, you know?
Okay.
So if you can repeat the last kind of 30 seconds, would be great.
Sure.
Thank you.
Yeah. So Penman-Monteith is a popular approach named after these two individuals because they really brought two key innovations to modeling ET. First, we can estimate evapotranspiration using climate data. And then Monteith later eliminated surface temperature from those surface energy balance equations because surface temperature is difficult to measure at scale, and then demonstrated how to estimate canopy and aerodynamic resistances, which are a reflection of the key role that vegetation canopy plays in regulating evapotranspiration. And with those two innovations, we became able to use gridded climate data and satellite remote sensing to estimate ET at large scales, regional, continental, and now global scales. And this is really possible from a modeling perspective because of two big ideas. So Penman-Monteith, what it really does for us is it helps us determine how much energy is available to vaporize water, and this is based on conservation of energy. And then there's a stopping criteria. So we start vaporizing water, and then we stop vaporizing water when the air is saturated. Those are the two big ideas behind Penman-Monteith. And the Penman-Monteith model is behind the model that I'm going to talk about in more detail today, the MODIS Mod 16 evapotranspiration model. This is a modified Penman-Monteith approach that provides global 8-day evapotranspiration and potential evapotranspiration at 500-meter resolution. And it's been available since the year 2000. We recently did a comprehensive recalibration and validation of this model for MODIS Collection 7, and also extended this model to the VIIRS sensors, which are aboard 3 different satellites operated by NOAA. And so now we know that we can continue these estimates, these global estimates of evapotranspiration through the year 2030 and beyond. So how we did that? Well, we combined Mod 16 with measured plant traits. So this is actually an example from Mod 17, which I'll talk about in a moment, but we did the same thing to improve these models because these are physical models. One of the other advantages of process-based models is that they're capable of incorporating parameters that you can measure in the field. So specific leaf area is a parameter in Mod 17, for instance. We can go and measure that in the field, and that can inform and improve our model. So these are examples of a probability density function for specific leaf area. And you can see, as we'd expect, savanna plant species, cropland plant species, they have higher specific leaf area. And the distribution of those plant traits is reflected in that. Leaf maintenance respiration, that's going to be higher in acquisitive species that are associated with croplands and herbaceous species that are associated with grasslands. And so we see that in the cumulative density for leaf maintenance respiration. I didn't have to go measure these plant traits. I'm an ecologist, but not an ecophysiologist. I was able to download thousands of these species observations from the global TRI database of plant traits. So this is a wealth of information about what plants are actually doing that we can incorporate into our models. And we know that this improves our models because we can look at something like, in the case of Mod 16, we are able to actually partition evapotranspiration into transpiration, into soil evaporation, and into canopy evaporation. But we don't actually calibrate those different partitions. We don't have a way of doing that, really. And so we don't tune those fractions, but when we incorporate these plant traits, we notice that we see improvement. So on the left-hand side here, this shows the previous version of MODIS Mod 16, which was known to overestimate soil evaporation and underestimate transpiration. And you can see that there's the gray bar.
I think we're having it again, unstable internet. We will ask Arthur again if he come back to tell us more.
fraction of ET
Arthur,
after you expect?
I
Yeah.
need to cut you again and to
Okay.
ask you to go back for 10 or 20 seconds back because of the
Okay.
internet. Yeah, thank you. Sorry for that.
Yeah, no problem. Um, okay. Is this a good place to start?
No, no, the other slide was good.
Oh, okay.
Yeah, yeah, yeah. It was just like
So
10, 20 seconds.
yeah, so we know that including real plant traits improves the model because it improves things about the model that we didn't specifically try to change or specifically calibrate. And one of those is the partitioning of ET into transpiration, soil evaporation, and canopy evaporation, or the green, gray, and blue bars in these plots. In the previous version of Mod 16, we were overestimating soil evaporation and underestimating transpiration in these ecosystems. But after including these measured plant traits, we see improvement in those fractions, more in line with what we would expect on average from these ecosystems. Now, one of the limitations of Mod 16 and most ET models is that we don't include soil moisture. When these models were developed, we didn't have global gridded estimates of soil moisture. It's actually only in the last decade or so that we've had access to globally gridded soil moisture data. And this can be a problem because we don't know how much water is available to vaporize. And the classic view of evapotranspiration schemes depicted by this figure, there are basically three different evapotranspiration regimes depending on how much soil moisture is available. If there's a lot of soil moisture available, we're actually limited by energy. The amount of ET flux will only increase if there's more energy input to the system. This is a very wet and likely saturated system. But at some point, we reach a critical soil moisture below which, as it gets increasingly dry, now we're in a soil moisture limited regime where we have enough energy. Energy is not limiting how much evapotranspiration can be produced. Really, we're in that soil moisture limited regime. And so the critical soil moisture is one parameter we might want to understand when we're modeling the effect of soil moisture on ET. And then there's also the wilting point, which is basically when there's no more water that can be extracted from the soil by plants. And there we see ET really virtually ceases at that point. So how do we get soil moisture into ET models? Well, in Mod 16 and in PTJPL, we don't have soil moisture, but we do have something like it. These models have long assumed that the near surface soil is in equilibrium with the air. So if you have drier air, you have drier soil. And this is generally true on longer timescales. It's obviously not true on short timescales. So that would look something like constraining this flux with a soil moisture function that is proportional to the vapor pressure deficit. This is, again, a necessary simplification because we didn't have gridded soil moisture data. When we look at models, again, like PTJPL, which has not had soil moisture, but in a recent version started to include soil moisture, if we look at the difference between the model without soil moisture and with soil moisture, we see that generally we do have an increase in water flux from ecosystems, from a number of ecosystems that are not energy limited. But the difference in that lower left-hand plot in terms of energy units, watts per meter squared, this difference is actually within the error of our ability to measure ET fluxes using eddy covariance towers. So soil moisture could be an important constraint, but we're not actually seeing that in the models just yet. Um, Now, Mod 16 is at 500-meter resolution. Many of you are probably more interested in field scale, much finer resolutions. I'm happy to report that Mod 16 has been applied at field scale. And this is enabled by the fact that we partition the radiation that reaches the canopy or reaches the soil using a measure of canopy closure, of canopy FPAR, similar to leaf area index. And that's derived from the MODIS satellite and the operational derive that measure of canopy closure from higher resolution platforms like Landsat. And in fact, that's what one of my colleagues did in 2019 and was able to use this robust model to estimate evapotranspiration at finer resolution. Now, the OpenET ensemble, which you may be familiar with, of course, the main advantage of those models is that they are able to do this at field scale using high resolution data. And it's an ensemble of models. So every model has its weaknesses, has its biases, but when you combine all the models together, you can come up with an improved estimate. We were able to show that, yes, indeed, the OpenET ensemble is generally better for croplands because of that high resolution and because some of those models do have an irrigation supply constraint that Mod 16 does not. But Mod 16 performs similar or better than the OpenET ensemble in non-croplands, specifically forests, shrublands, savannas, and other types of non-croplands. So we're pretty happy with the performance outside of croplands. Now, I've been talking about water fluxes, but of course, water fluxes in plants, they share the same conductance pathway. It's these plant stomata that are depicted in this micrograph on the left, through which water leaves plants and carbon dioxide is able to enter plants. So this joint conductance to water and carbon dioxide is the basis for the tight correspondence between evapotranspiration and what are ultimately given as estimates of yield or production. And so I want to transition to talking about productivity models. So in addition to Mod 16, the Modis Mod 17 product was developed in my lab. This provided the first global weekly terrestrial production estimates based on the Earth observing system. This is an ongoing, this slide is a little out of date. We're approaching 25 plus years record of gross primary production and net primary productivity. And it has that same resolution that's really limited by the satellite platform that we have. And what we've been involved in more recently is trying to, again, extend this record from MODIS to the new VIIRS satellite sensors. So how does Mod 17 work? Well, this is that Jarvis-Stewart framework again. We don't, for this operational model where we want low latency, kind of near real-time estimates of GPP and NPP, we don't know the exact functional form of the constraints on GPP, but we can create a function that helpfully describes the limitation of GPP due to minimum temperature or vapor pressure deficit. Those functions limit this kind of upper rate or maximum rate of solar energy conversion. So this approach is referred to as a light use efficiency model. With GPP, we're then able to estimate an annual rate of net carbon assimilation by subtracting the plant's metabolic respiration. Now, how do we justify using a light use efficiency approach? Some of you agronomists, maybe some ecophysiologists, you may know that there's actually a nonlinear dependency on irradiance and on available CO2 inside plant mesophyll. And at some point, you don't just get an increasingly linear increase in net photosynthesis with more CO2 and more light. There's underlying biochemical limitations to the reuse and recycling of ribulose biphosphate and other compounds. So how can we have a linear model when there's actually a nonlinear relationship between photosynthesis and some of these drivers? Well, when we do this at large enough spatial and temporal scales, we actually do get a linear response. And that's because of the distribution of photosynthetic efficiency throughout a canopy. Leaves towards the top of a canopy are generally younger and have higher rates of photosynthetic efficiency. And so what we see, particularly if we compared sunlit leaves and shaded leaves, we'd find that the total net photosynthesis is much similar to a linear function. And so as long as we're applying this at the appropriate spatial and temporal scales, we're getting a good kind of linear approximation of daily to weekly primary production. And I'm happy to report that we can do this at field scale as well. So again, one of my colleagues taking that same approach that we saw with Mod 16 was able to downscale these model estimates to field scale that is closer to Landsat resolution by using Landsat imagery in place of these more coarse scale, these moderate resolution measures of canopy closure. Okay. And that's actually the basis for our estimates of rangeland productivity. So some colleagues of mine working in this lab have spent years developing a measure of rangeland productivity. And this is essentially based on Mod 17. They've used a suite of machine learning algorithms to map vegetation cover, to map the fractional vegetation cover among different annual and perennial grasses, among shrubs and trees. And then we're able to convert that grass, those grass fractions in particular, into above ground biomass productivity, so that ranchers and other landowners can understand the forage quality and forage quantity that's available for livestock. And this is an example of what that looks like. You can check out the map yourself at rangelands.app. This map is only available in the contiguous United States, but again, this is just an application of Mod 17. This is a fairly straightforward application. It is underpinned by these machine learning estimates of land cover, fractional land cover change, but the model itself is fairly simple. So it's something that I think certainly could be applied to other regions. I want to transition to talking about the third kind of model that I've been working with lately. You may remember Mod 16 and Mod 17 are missing a key constraint on ecosystem productivity and ecosystem water fluxes, and that's soil moisture. Now, fortunately, NASA has an entire mission dedicated to mapping soil moisture, and that's the Soil Moisture Active Passive mission that was launched in 2015. This consists of a huge mesh antenna that is able to measure soil temperature and soil moisture twice daily everywhere across the globe. And in particular, I've worked with two models related to this mission, the level 4 soil moisture and level 4 carbon models. NASA describes these by level 4. What it means is these are model enhanced estimates of soil moisture, temperature, and the terrestrial carbon budget. So we take satellite measurements, we combine them with an ecological model or an ecosystem model, and then we get new estimates that we couldn't otherwise, things that we couldn't directly sense with the satellite itself. So for instance, one of the things that we've been able to do with SMAP level 4 carbon is monitor drought impacts. And this is an example from my part of the world. In 2021, due to a wandering jet stream, we had a severe high pressure heat dome, really persistent high temperature and drought conditions in summer 2021. In some areas, the measured temperatures actually exceeded 40 or 45 degrees Celsius, which is crazy, that truly the highest recorded air temperatures in that region. Some of you may know that this is actually a temperate rainforest, and I actually spent some time in the temperate rainforest during this extreme heat, and it was very strange to be in a very, very dry temperate forest where the ground is below you is completely dry. And many people observed widespread foliar damages in areas where these extreme temperatures were experienced. This time series plot here shows some smooth data from the daily level 4 carbon budget GPP estimates, and we can see that there's an extreme negative GPP anomaly associated with that Pacific Northwest heat dome. It's actually the largest negative GPP anomaly in this region. And of course, this is a satellite product, so we can also produce a map of that. This shows the monthly GPP anomaly for July 2021, and we just compared that to the US Drought Monitor map. Now, the US Drought Monitor, this is a rather subjective product where meteorologists get together and they use their expert knowledge to kind of draw these drought contours. We wouldn't expect it to correspond perfectly to SMAP level 4 carbon, but we do get a really nice distribution of the impacts of the drought on GPP due to this event. Now, if we take that one step further, as one of the PhD students in my lab did a few years ago, we can actually start to estimate drought impacts on crops. And so what Patrick Worcester did in 2021 was to take GPP estimates from level 4 carbon and compute a cumulative GPP climatology for, in this example, corn in the US Midwest. So the corn has these specific phenological stages. We would expect GPP to reach a certain value at each stage. And what we can do then is take this long record of GPP and look at the anomalies in GPP. So where GPP deviates from that cumulative GPP curve, and convert that into an index of the drought impact on this crop or the crop condition. And working with some colleagues who had actually developed a statistical index of crop condition, we were able to show that this works really well for certain phenological stages in corn in the Midwest, where we have strong correlations between this index and what is field observed crop condition, the crop condition reported by farmers. So they're agreeing with this index. And in particular, this index works really well in semi-arid regions. It works less well in humid regions. We suspect that's because of the importance of soil moisture in our model. These soil moisture measurements from the SMAP satellite, they just provide such a strong constraint in those semi-arid regions that ultimately it provides better model predictions. And one other thing that we can do with the level 4 carbon product is we actually are able to estimate the soil organic carbon state, which is the most important determinant of soil health. So we get soil organic carbon because we're computing a full daily carbon budget. We're accounting not just for that productivity flux, the flux of carbon into terrestrial ecosystems, but we're also calculating the respiratory flux of carbon leaving these ecosystems. And that allows us to quantify the net carbon balance, which is actually just the time change in soil organic carbon. So ultimately, we can estimate parameters like soil organic carbon and the mean residence time of carbon, which are both key determinants of soil health. And finally, I've talked a lot about some pretty big data sets, some pretty complex models. And so you may be very interested in these topics, but you don't exactly know where to start. I'd also like to advertise some work that I've been doing with Walid, the workshop organizer here. Walid actually organized a workshop last year in Algeria where we presented some of the material from our Open Climate Science for Agriculture curriculum. So this is a NASA-sponsored project where we develop free and open source materials, learning materials that are online that introduce you to how to use NASA data, where to find it, how to work with it, how to process the data in a reproducible way. And the materials right now are being translated into French and Arabic. We actually have the first 3 models already translated into French. We'll have the first module translated into Arabic very soon. So if you're interested in learning more about the data and the tools that we use to analyze the data, I do suggest that you check out our website. And again, I can't thank Walid enough for helping to organize this workshop that we held in Algeria last year. So this is something that we'd love to do again. You know, this was a smashing success where we had a number of participants, all scientists from around Algeria, northern Algeria in particular, who got to get their hands on NASA data and actually start working with it to understand climate variability and its impacts on agricultural ecosystems. So with that, I want to thank you all for attending this workshop. If you have any questions, please reach out or ask them now. And then, of course, please connect with us at openclimatescience.github.io.
Thank you so much, Arthur. Thank you so much. I really appreciate the new development that you're having with the GPP models and the Mod 17 and the all the SMAP L4, something that I mean, I'm following, but I didn't really um, hear recently from you. So please, if you have any questions, you can use the Q&A or just put it in the chat. One of the questions that I usually have, so it's basically the how accurate and how usable is the soil moisture data, especially from the SMAP mission, like at the agricultural level. I don't know. Yeah, please. I don't know.
Yeah,
What do you
so
think, Janelle?
yeah, so our target for the level 4 soil moisture product is 0.04 cubic meters per meter volumetric water content. That's our estimated accuracy for level 4 soil moisture. But that is compared to some ground soil measurements largely throughout the US Midwest. So I know that some people have done some other work validating level 4 soil moisture in other parts of the world, and also in validating the level 3 product. The difference between level 3 and level 4 actually is a land model that takes in satellite observations, the SMAP, brightness temperature measurements, and it attempts to model what the satellite sees by perturbing the soil moisture state. So it basically makes a guess as to what the soil moisture is. Then based on that soil moisture, it can model what the satellite would have seen. And it does this iteratively to just try and minimize the difference between what it thinks the satellite sees and what the satellite actually measured. The advantages of doing this is that it can incorporate other sources of information, combining them with the satellite measurements. So you get kind of an average of multiple data inputs and the satellite measurements. It also allows us to propagate that what is essentially a surface soil moisture measurement that the satellite sees, its penetration depth, which varies with the amount of vegetation present, is between 5 and 15 centimeters at most. So if we really want to, what we do for SMAP level 4 carbon, of course, is we're interested in the soil moisture at the root zone, which is about 1 meter depth. And so level 4 soil moisture allows us to, being a land model, it allows us to propagate that soil moisture down to the root zone level. Now, the root zone estimates are less accurate than the surface estimates because they are modeled. But again, what we see in, I guess, the subhumid kind of, Oklahoma mesonet comparison is 0.04 cubic meters per cubic meter.
Cool. Thank you so much. I mean, we're open for more questions. And I wanted just to follow up on what Arthur was saying about the workshops. Actually, that's how we come up with this workshop with 6 grain, because actually we have been like doing it we did it in Algeria, and we have done multiple also in Algeria. But then we thought that we need to extend it more for like more practitioner and more people who are like at the government level. So, and as you know, like everywhere um in the global south mainly, if there is any interest for us to come like with 6 grain and the open climate science to the country level, and if there is any governments that like representative that can help us get in, that will be we are super happy to do it, and all the 6 grain or UMD team will be very happy to come.
Yeah.
So you have
I'd
another
like to
question. Go ahead.
respond to the question, yeah, about transformer-based deep learning models. Yeah, I think that's really exciting, particularly because with that transformer-based approach, you're able to do something that a lot of machine learning models don't do, which I alluded to. The things that makes it easy to surprise the machine learning models is that they don't have a memory. They don't incorporate kind of lagged responses or lag sensitivity. And soil moisture, of course, as a field, has a lot of memory. So I think it's exciting to use transformers because you could have something like a recurrent neural network or a long short-term memory network as part of that to predict evapotranspiration. As far as the input data sets to remote sensing, I would go back to that surface energy balance and go back to the micrometeorological physical models. So look at what are they using. So we know that surface temperature is really important. We weren't able to measure surface temperature across the globe back in the early to mid 20th century when some of these approaches were developed. But now we have satellite remote sensing of surface temperature and canopy temperature. So that's really important. Using gridded climate reanalysis data. So getting that shortwave radiation, getting that net long wave radiation from gridded climate reanalysis data sets. Those would be really important inputs. Anything that you are able to represent about the vegetation canopy, of course, too. This depends a little bit about the spatial and temporal scales that you're thinking of modeling. But if you're trying to develop a machine learning approach, I would go to the physical theory and go to the physical models and look at what are the important constraints, what are the important inputs to those models, because they're based on years and years, maybe over a century of field work and theoretical work on thinking about evapotranspiration. So those would be key sources of insight into what should go into your model. Yeah,
So
Molly.
cool. Yeah,
Can
go
I
ahead, Molly.
ask the last question because we need to move to our next
Mhm.
thing? Which is, have you been working with the VIIRS data with the new, you've been working with MODIS for 1,000 years. Can you say a few words about VIIRS and whether
Yeah.
or not it's like seamless, or do we have to watch out for something?
Yeah, if you're interested in using Modis Mod 17 and extending that record with VIIRS, in the new Modis Mod 17 Collection 7, it is specifically designed to be seamless with VIIRS VNP 17. I'll put that in the chat. Collection 2. So Modis Collection 7 and VIIRS Collection 2. For GPP and MPP, those are designed to be seamless. I would encourage you to test that yourself, though. If you're working in a specific region, I would look at those two time series and just make sure that they correspond. They're designed to correspond together. We didn't do that for Mod 16 and VNP 16. So the VIIRS models are based on the same numbering scheme. So Mod 16 and VNP 16 are the same algorithm, but we didn't do any built-in bias correction there
Right,
because
and
there are
it's
lots of different,
significant.
yeah,
There are a lot of differences, like the reset and all the rest of it, the bands, and
yeah. The
it's
thinking with
really
that was,
complicated. Yeah.
yeah, the thinking with that was that there are so many different approaches, and there's pretty good documentation on different approaches to bias correction. So people should probably do that themselves. If you want to join these records together for ET, you should develop your own bias correction methods. VIIRS as a sensor is going to provide slightly less accuracy at very high latitudes and in the tropics, just due to the bandpass characteristics, but also it's an afternoon overpass as opposed to a morning overpass. And we prefer the morning overpass for those humid tropical regions because there's less cloud cover, less water vapor. So that is a problem with VIIRS. But VIIRS otherwise is extremely similar to MODIS.
Thank you so much.
Bon, thank